We recall that the effective stiffness matrix takes this form in the case of orthotropic composite structures. Recall that if we wanted to compute this effective parameter, then we made the normal strain in the one direction in average equal to 1, and all other average strains in the other directions, in the normal strain in the 2 direction and the 3 direction, and all the shear strains, the average of all the shear strains were put to equal to 0. Physically, this means that we stretch a representative volume element in the x direction such that the structure becomes twice as large in the x direction and make no other changes in the other directions. We don't need to deform the whole composite structure. It's enough to consider just this representative volume element and stretch it. Then we obtain the following problem. We just stretch the structure in the one direction and do nothing in the other directions. Recall that in order to find the coefficient C11 star, we just compute the energy in the case when we let the normal strain in the one direction be equal to 1 in average. We may use another value for this. We may stretch it so that it has the value k instead. Then it's very easy to see that we just get k square here and k square in the denominator. So this changes, but of course the parameter is the same, but the energy will be changed. So this is a general formula. For numerical estimation of this parameter, we can of course use k equal to 1, but if we are doing some tests on the composite material, we have to use a much smaller value. Otherwise the composite material will be destroyed. Recall that we also can compute this effective parameter by computing the average normal stress in the one direction. And you easily see why. If we just multiply this 6.6 matrix with this vector 1, 0, 0, 0, 0, 0, 0, then we obtain the vector on the right hand side, which consists of 3 non-zero elements, and the first of these elements is just equal to the average normal stress in the first direction, as we see on the right hand side of this, the left hand side of this equation, and the other two are just equal to the average stresses in the second and third direction respectively. If we want to compute the next column in the stiffness matrix, we do as we suggest on this photo. We stretch the structure in the y direction, in the x2 direction, and make no average changes in the other directions. Multiplying this stiffness matrix with a new average strain vector, we obtain the vector on the right hand side, which now is equal to the average stress vector on the left hand side, and therefore we know how to find this parameter in the same way as before. The third column in this stiffness matrix is found similarly. This effective shear modulus in the 1-2 direction is found by putting all the average strains equal to 0 except for the average shear strain in the 1-2 direction. So then we obtain this problem, and we find that the effective shear modulus in this 1-2 direction is found by making a shear strain like we see in the figure. And this can be done either by a numerical computation or a physical experiment. In the case of periodic structures, it's possible to use the period of the cell as the representative volume element. In cases when the structure in addition is symmetric, as we see here on this figure, we see that the deformed structure will inherit this symmetry. So in this case it's possible to use Dirichlet boundary conditions on the boundary, and the Dirichlet boundary conditions may be chosen such that it's equal to 0 on one part of the period, for example, and a constant value on the other side, depending on which effective parameter we are interested in finding.